Hello and welcome to the Logit and Probit model tutorial series by Spur Economics. We often encounter dependent variables that are continuous in nature, such as income. However, dependent variables are not always continuous or quantitative. We often have to deal with dependent variables that are qualitative in nature, where we have dummy variables or categorical variables instead of continuous. Let us consider a simple example of an individual owning a car. In the equation shown here, the dependent variable is x, which represents whether an individual has a car or not. This variable is a function of independent variable income, that is, the ownership of a car depends on income. If an individual owns a car, then x is equal to 1. On the other hand, x is equal to 0 if an individual does not have a car. Therefore, the dependent variable x is a binary, categorical, or qualitative variable. When we estimate this model using ordinary least squares or OLS, it is known as the linear probability model. The probability of success, probability of owning a car, or probability that x equals 1 is a linear function of independent variables. The predictions from this model will represent the conditional probability of an individual owning a car, given his/her income yi. This is because x equals 1 is a situation where the event will occur and the individual owns a car given his/her income. We can easily include other independent variables in this model, such as price of fuel, daily distance traveled, marital status, and others. From this example, it seems that applying OLS in such cases and estimating the linear probability model is a good idea. However, this approach suffers from some serious problems. We know that the probability of an event lies between 0 and 1 and it cannot exceed these limits. However, the application of OLS in the linear probability model can lead to the predictions of probability that exceeds these limits. Suppose beta 1 is estimated to be 0.2 and beta 2 is 0.0005 in our car ownership example. Then, at $1,800 income level, the predicted probability of success or probability that the individual owns a car will be 1.1. We have a probability greater than 1 which does not make sense. Therefore, for certain values of income, the probability may breach these limits of 0 and 1. A negative probability or probability greater than 1 does not make any sense. We can use a few different ways to deal with this problem. For example, we could decide to simply take negative values as 0 and values higher than 1 to be 1. Another method we can use is to make predictions by creating values of 0 and 1. For instance, we can consider all predicted probabilities less than 0.5 to be 0. Similarly, all predicted probabilities equal to or greater than 0.5 will be taken as 1. This way, we will be predicting the ownership of car based on a probability cutoff value of 0.5. However, having a negative or greater than 1 probability is still not appropriate. The linear probability model or LPM suffers from the problem of heteroscedasticity. The error variance in LPM can be expressed as shown here. We can see that the variance of the error term is a function of the probability of success. Further, the probability of success is a function of independent variables in the model. As a result, the error variance is also a function of the independent variables. Homoscedasticity or constant variance of error is one of the important assumptions of OLS. The tests of significance are no longer valid if this assumption is not met. We observed earlier that the error variance is not constant but a function of independent variables in the case of LPM. Due to heteroscedasticity, OLS estimates are still unbiased, but they are no longer efficient. In fact, the OLS estimates are asymptotically inefficient. We can consider the use of weighted least squares to solve this problem of heteroscedasticity. Also, we can make use of the robust standard errors or White's heteroscedasticity consistent standard errors, but it still leaves us with other problems associated with the linear probability model. Now, let us move on to the biggest limitation or problem of the linear probability model. The LPM assumes a linear relationship between the independent variables and the dependent variable. In our example, this means that the ownership of a car is a linear function of income. This implies that an increase in income always leads to some constant increase in the probability of owning a car, irrespective of the income level. Therefore, it does not matter whether income increases from 100 to 101 or from 1000 to 1001, the probability will increase by the same constant amount with a 1-unit increase in income. For example, let us say that income increases by $100 for two individuals. Their initial income level has no effect on the probability of owning a car, and the increase in probability will be the same for both. It does not matter whether income increases from $100 to $200 or from $10,000 to $10,100, probability will increase by the same constant amount with a 100-unit increase in income. This is not realistic because the effective income on ownership of a car will not be constant throughout different income levels. At very low levels of income, the increase in the probability of owning a car should be low. After all, the individual may still not be able to afford a car. Beyond a certain income level, the increase in the probability of owning a car will be higher with an increase in income. Similarly, at very high income beyond a certain level, the effect of a small increase in income may be little on the probability of owning a car. Hence, the probability of owning a car may be mostly unaffected by income changes at very low or very high income levels. This means that a linear model is not enough to explain such relationships, and we need a nonlinear type of function. At extreme levels of income, that is very low or very high income, we need the probability to change slowly with small changes in income. When income is not at extreme values, the probability should change relatively faster with small changes in income. In the next tutorial, we will introduce two such nonlinear functions that can help us overcome the problems associated with the linear probability model. Thank you for watching, and I will see you in the next tutorial.